Okay, so what I wanted to do today was to give a little bit of motivation about how we can think about using large-scale structure surveys, CMB surveys, in ways that go beyond the sort of, I guess, the standard and conventional ways we have been thinking about using those data, and in particular in the context of looking at dark energy and testing gravity on cosmic scales. And I'm going to try and give you a taste of three recent papers that have come out in December and January this year that help motivate that. And these have been led by, not by me, but by graduate students, postdocs and undergraduate students working at Cornell. And so I will give them due credit as we go through each of those three. It's down to their work that these interesting papers have come out. I'm going to first start talking about some work on the kinetic Sunyaev-Zeldovich effect, which I know many of you, including Colin, know all too well, but give you, those of you who don't work in that area, give you an idea of why we're very interested in using that technique. Then I'm going to talk about how we can use, we might use spectroscopic surveys not to look at clustering regions, but to look at void regions and use those as interesting environments for testing gravity. And then finally, I'm going to talk about some recent work we have done looking at how you can combine different traces together to try to offset and have an interesting interplay between different scales, different traces, and different redshifts to try and put constraints on gravity. Okay, so the whole motivation of this is to really understand the origins of cosmic acceleration. And of course, this has been an effort for now over 2 decades, trying to understand where the modifications to Einstein's equations need to come in order to explain cosmic acceleration. It could be a cosmological constant, but we still have not understood why that value, the observed value, is 120 orders of magnitude smaller than those predicted by theory. It could be a different type of matter that evolves in redshift that is not something that we are able to observe here terrestrially, or it could be that we just don't understand gravity in the cosmological scales and density in the environments that we observe these cosmological observations in. And so large-scale structure surveys, both within the last couple of decades, but now I'd say, really moving to a much larger scale in the coming decades. So with Rubin LSST, with DESI, with Euclid, with Roman, and with upcoming CMB experiments like the Simons Observatory that the Flatiron is heavily involved with in CMBS4, will be provide powerful, unprecedented data to test which aspects of this theory space hold true. And it comes through, sampling a variety of spatial scales, different cosmological environments, and redshift scales. And each of these observations that we'll be talking about provide different facets to understand this conundrum, and also in combination. So my elephant at the top is, coming from the parable of how do blind men understand an elephant? You all have to look at different aspects of it to get a full picture. So, of course, we understand gravity extremely well within the solar system, but as the gravitational wave astronomy push has also made, we need to understand the properties of gravity not just in our solar system environment, but also in other parts of that parameter space. So here is a really nice plot I like from Demetrius Saltis a good few years ago now, which shows that if we really want to understand gravity, we can't just localize it into thinking about the gravitational potentials and the curvatures that are experienced within the solar system. We really need to push it to all the regimes. So we can think about the compact object regimes probed by LIGO. We can think about the galactic centers probed by the Event Horizon Telescope. But cosmology also allows us a different window onto the properties of gravity that these high density, high curvature regimes don't give us an insight into. And so it really is a complementary observational window that we shouldn't presume we know how it's going to behave in those environments by looking at other very different situations. So in terms of the work that's gone on to date in looking at dark energy, we can really think about three classes of observables. The first are looking at the homogeneous expansion and looking at geometric measures to understand the expansion rate. So things like the angular diameter distance inferred from the CMB last scattering, supernovae luminosity distances, baryonic acoustic oscillation, characteristic scales imprinted in galaxy clustering, and strong lensing time delays. But then we can also use large scale structure to not look at the homogeneous, but look at the inhomogeneous effects, or the effect of gravity and dark energy on inhomogeneities. There are two real ways we can do that. One is to look at measurements of the growth rate of history through biased tracers that allow us to get a sense of how the gravitational potential has evolved up to some normalization, namely how those tracers are biased relative to the underlying dark matter field. And that includes looking at the distributions, the number counts, the velocities of galaxies and galaxy clusters. But then we can also get direct measurements of the gravitational potential through the integrated Sachs-Wolf effect in the CMB on large scales, CMB lensing, and galaxy cluster lensing, which in theory give us a direct measurement of the gravitational potentials, although arguably integrated along the line of sight. So what I wanted to, part of the message in this presentation today is that an individual survey, an individual probe doesn't give you the full picture. And what we want to do over the coming decade is leverage trade-offs and complementarity across the many LSS, the large scale structure and CMB surveys. We want to be able to contrast the ability to get photometric speed and imaging with the spectroscopic redshift precision of spectroscopic surveys. We want to trade off the survey area of Euclid with the depth that we're going to see with the Roman W first survey. We want to see repeated overlaps of different surveys surveying the same region. And we want to see the effect, to be able to remove the effects of like dithering and cadence from an individual survey and overlap what we can see of the underlying cosmological maps by comparing different observations. We want to contrast the precision that we get from space with the larger sampling that we can see, the survey areas from the ground. We want to use multiple astrophysical tracers, different mass levels, different environments, different redshifts, and we want to combine all of those to get the fullest picture we can. And in combination, therefore, the idea is that these individual surveys can actually give us a richer set of observables to be able to understand not only cosmology, but of course, extract out the astrophysics and go beyond any individual survey's potential. Okay, so with that motivation, then I'll start just talking about the first paper that, and it's actually a pair of papers we brought out recently as part of the ACT collaboration. And I'm going to talk about one paper in particular, which is a measurement of the pairwise kinematic Sunyaev-Zeldovich effect using the ACT data with Sloan spectroscopic galaxies. And this is work that was led by Victoria Califort, who is a graduate student at Cornell, who's now at CETA, Patrizio Gallardo, who was a postdoc at Cornell and is heading off to Chicago, Eve Vavradiakis, who's a graduate student at Cornell working with Mike Niemak, and Stefania Anamadeo, who's a postdoc working with Nick Battaglia. So say Patrizio Pato is working with Mike Niemak too. And so this work came out in January. So it's focused on an observable called the kinematic Sunyaev-Zeldovich effect. And this, for those of you who are not involved in this field, is essentially a measurement of the Doppler shift of clusters, of galaxy clusters, seen through an imprint of that Doppler shift on the CMB relative to its rest rate. So if you have a CMB photon, it interacts and scatters with those energetic electrons within the intracluster medium. And if that cluster has a peculiar velocity along the line of sight towards us relative to the CMB rest frame, it induces this blue shifting or a Doppler shift. And so that is encoded in essentially a temperature decrement or excess, depending on the peculiar velocity, imprinted in the CMB. So this is one of a number of Sunyaev-Zeldovich effects coming from clusters. The other most famous one is the thermal Sunyaev-Zeldovich effect, which comes from the heating of the CMB relative to the by the hot intracluster gas. On the right here is a plot just showing the frequency dependence of the thermal SZ decrement or increment change relative to the kinematic one. And you can see that because the thermal SZ is essentially a shifting in the black body spectrum as you heat up the CMB photons, you end up with an excess in the high frequencies, and the 0 point is about 220 gigahertz, and a decrement at lower frequencies. And so surveys like ACT that have multi-frequency bands are able to use those multi-frequency bands to extract out the thermal SZ signature and get thermal SZ detected clusters, for example, through that technique. In comparison, the kinematic SZ is a much smaller effect. It's about a factor of 10 smaller, but it also has a really weak frequency dependence, which therefore presents challenges in how you extract it. So the way that we look to extract it is to utilize the fact that these the KSZ is coming from motions of clusters, and those motions of clusters are correlated with each other. Essentially, we expect clusters to be infalling relative to their gravitational potential, to be gravitationally attracted with each other. And so we expect there to be correlations in those peculiar velocities between the clusters. So if we look at the pairwise correlations, the pairwise infall of those clusters relative to each other, that should be something that allows us to extract out this effect. And we identify the clusters typically by identifying optical members of the cluster as proxies. So we use optical surveys to identify luminous red, typically red galaxies in those clusters to identify and locate both in spatially and redshift space where those clusters are. Once we have identified those clusters, we would then, or the cluster locations, we then use aperture photometry to extract out the temperature of that cluster. And so this just gives you a little stepwise example of how we do that. We use that galaxy proxy to center the cluster, to determine a center of the cluster. And we typically, what we do is take the most luminous galaxy as the most massive galaxy, and we assume that is in the center of the gravitational potential of the cluster. There are astrophysical realities that is not perfect, and we can get miscentering errors, but let's take that aside at the moment. We then, around that center, will calculate an aperture photometry by considering the average temperature within an aperture and then differentiating it from an annulus around that aperture to be able to subtract off the background CMB. We then take into account the fact that we want to get, we want to subtract off sort of thermal SZ contributions. Now we don't expect that the thermal SZ will have the same characteristic correlations, right? So when we look at that correlation, all of these contributions to the cluster temperature should be suppressed in that signal. But we might anticipate that if there's evolution in the TSZ because of redshift, then we might, if there's a little bit of an increase, then we might expect that perhaps could mimic it. So what we do is we smooth over the temperature within those apertures across a particular redshift and weight it by the redshift differences and subtract that off in order to get a temperature decrement. We then use those temperature decrements to calculate this pairwise KSZ using geometric factors to account for the radial co-moving separation between the clusters. Okay, so before I start talking about how those observations have come about with a number of surveys, I just wanted to say that the intent here is to connect those observations to underlying theory, to cosmological theory, and we do that by making predictions of what we expect that pairwise decrement to be for a particular cosmological model. So on the right here you can see this p-hat theory. This is saying that the pairwise momentum is going to be related to the pairwise velocities of the clusters multiplied by the optical depth of those clusters with a ratio of the temperature in the CMB and the speed of light. And so the idea is that if we have observations with knowledge of the optical depth of the cluster, we might be able to backtrack out then an estimate of the peculiar velocity and use that to constrain cosmology. And that expression there, that V is that pairwise velocity, and it has a number of dependencies that have cosmological information, including the linear growth rate, F, the Hubble rate, they're giving redshift, and then clustering information from the halo correlation function. And one of the key parts of this is that, of course, these clusters are a biased tracer of the underlying dark matter. And so we need to be able to model the bias functions and understand what the mass sample is for those clusters. So that's another piece of theory that has to go in there, nuisance parameters. Okay. So in thinking about where we want to head with this and the potential, the cosmological potential, a few years ago, Eva Marie Müller, who was a graduate student with me and is now a postdoc at Oxford, Francesco De Bernardis and Mike Niemek, we did some work sort of forecasting what the potential could be for this approach using stage 3 and stage 4 surveys. And what we found was this was actually a very nice complementary way to test, for example, the growth rate and also constrain neutrino masses to, for example, other techniques using redshift-based distortions of galaxy clustering. And so there is potential here if we can understand, for example, the effects of the bias, the model the biasing, and get measurements of the optical depth to be able to get out some very nice underlying physics, dark sector physics here. So we've seen a number of pairwise kinematic results in recent years. We've seen them from Planck across, for example, the Sloan samples. We saw earlier ACT results from Hand et al. With Boss and from Francesco de Bernardis et al. With another earlier Sloan sample. And we've also seen it with photometric surveys from SPT, South Polar Telescope CMB, across the Dark Energy Survey. So there's been very nice sort of track record of utilizing different increasing galaxy samples and also photometric and spectroscopic samples to extract out these effects. So our work this January was taking this to the next step, utilizing sort of 5 years of ACT data and using the most recent releases of the Sloan luminous red galaxy spectroscopic samples to take 340,000 galaxy LRG proxies, and the redshift distributions are shown here, out to around redshift 0.8, but averaged around redshift of 0.5. to get this pairwise KSC effect. And what we did was look at various luminosity cuts of these clusters estimated by connecting the luminosity of the proxy galaxy to the luminosity of the cluster. So we tried to look at them in different mass spins to see the effect on the signal. Oh, I should say actually, so in addition to single frequency results, so at 90 and 150 gigahertz with ACT, what we also did was use a multi-frequency map that combined Planck and ACT data in an internal linear combination map as well, to compare different, so the effect of taking single frequencies and looking at the effect of foregrounds on that, and then looking at an internal linear combination map. So here is just as some of the results that we found, and you can see this. This is showing essentially this correlation where you're seeing a peak in fall, a correlation between the clusters at around sort of 30 to 40 megaparsecs, and a distinctive signal, multi-signal signal that as you go to higher separations, you tend towards no mutual correlation of infall. And this is for 3 different luminosity builds. So the top one is for the full sample that we considered. So it has the smallest error bars, and then we take a higher luminosity cut and a higher luminosity cut again cumulatively, so they all have the same upper bound. So as we go to the lower plots there, the noise gets bigger because the sample gets smaller. But what you can see here is for the comparison results for the same galaxy sample, but the 3 separate maps. And what you can see is very nice consistency in the predictions for the 3 separate maps. One thing I wanted to touch on that Patrizio Gallardo was looking at how we estimate the errors, the uncertainties in these signals. Often these are the way in which so there's 3 ways we could do this. One is to create noise simulations of the survey and look at the covariance across those different simulations. Another is to sample from the data itself, which in theory then means you've included all the possible uncertainties. You don't have to be restricted by how well you modeled it in the simulation. Frequently that's using jackknife sampling, where you remove a fraction of the sample and recalculate the signal and calculate the covariance once you remove the signals, the subsamples multiple times. An alternative is bootstrap resampling, where you essentially randomly reassign temperatures with replacement. And so we did jackknife analyses first, but what then we realized was that it was underestimating the uncertainties. And so this on the right hand side here is showing the distribution of chi-squareds using a jackknife resampling, which is the blue curves, the bootstrap resampling, which is the orange curves, and then looking at the distribution from noise simulations that we had. And you can see that the bootstrap resampling gives a much better unbiased measure for these pairwise velocity. And it may, and Pato conjectured that, I think it makes sense that, when you're removing one from a pair, but we're calculating a pairwise statistic, this is somehow altering the distribution. We need to, and so making sure there's a replacement remove that potential bias. But I thought it was a really interesting and neat piece of work that makes you think carefully about how you're estimating the errors for statistics that aren't just a simple count over individuals. So then we looked at putting constraints, comparing this with theory, and what we did was just use the Planck best fit cosmology, compare the observations to the theory to get an estimate of the optical depth, the average optical depths of the samples. So the plot here in the middle is showing you the data compared, and overlaid on that is the sort of best fit from the theory with the tau uncertainties, and on the bottom are the likelihoods of the optical depth measurements. And I think the nice thing here is showing the consistency of the optical depth estimates from the 3 different maps for a given galaxy sample, and the way in which you can see the optical depth is increasing as you go to the higher luminosity samples, so as we would intuitively expect. But we're not at the level yet of being able to know that optical depth and then push it to cosmological constraints. And one of the challenges we found was when we looked at the optical depth estimates from that comparison of the KSC measurements to theory, and we compared them with the optical depth estimates from the thermal SC analysis that Eva Vagiakis led in the partner paper, we found that these KSC estimates significantly lower than the TSC. And so there's a lot more work to be done to really understand how we can use these KSC measurements in the push towards cosmology. In particular, is this because the distributions of the signals with the KSC and TSC emission are just morphologically different? Is it that we need to understand the halo biasing, the halo mass estimation, the cluster mass estimation, how that's related to the proxy galaxies in more accurately? And so we're going to be doing some of the next steps are running these pipelines on simulated clusters, for example, the Websky sims, and trying to see whether we see the same thing there or whether it's something in the data, and then also trying to do some better understanding of how we get the cluster mass estimation. We can use alternative ways to get masses, for example, with cluster lensing or with red mapper photometric mass estimates. So there's lots of interesting work coming out of this. And it's motivated by the next generation of spectroscopic surveys and CMB surveys. So for DESI, CROSS-ACT and Simon's Observatory, DESI's taking its first data now. We expect the first year of DESI, so if it's going to be about a 10% survey, to be comparable with the analysis that we've just done in terms of the number of galaxies we expect to see. And so that's the perfect way for us to look at refining and honing that pipeline and to understand how the astrophysical and analysis systematics might be coming into play. But for the full DESI, and especially if we then move to Simon's Observatory as well, we're looking at an order of magnitude more galaxies. And so if we are able to refine this approach, it's the perfect transition to be able to do some of the things I talked about and move from astrophysical understanding of clusters towards constraints on cosmology. Okay, so I'm going to segue now to topic number 2. And this is work that's been led by a graduate student working with me, Chris Wilson. And it's looking at how to test for gravity in void environments. So not thinking about galaxy clusters, switching to the exact opposite now. And I've included both the link to the paper, but also a link to the GitHub repo where Chris has put all the codes and analysis for this. So just to give you an overview as we switch topics, voids are a really novel way that people have been starting to study novel environments that can allow us to probe potential deviations from general relativity. And people have thought about this in the context of void number counts, using void lensing in voids, but also these velocity statistics. And so the thing that Chris has done is to look at how galaxies in voids their motions and how that's affected by deviations from general relativity. And the work that he's done that I'll describe now is theoretical in nature, motivated from the simulations, but the next step is to really think about how we might be able to use spectroscopic galaxy surveys to make some of these signatures observable. So when we think about galaxy dynamics, we're thinking about their motion within the gravitational potential phi. And in the case of having modified theories that deviate from general relativity, we introduce an effective fifth force. So this second term on the right-hand side here is what we're in F of R gravity you're looking at as a gradient of this additional scalar mediation. And so we need to think about evolving both the Newtonian potentials that are due to the local density and this fifth force, which is an additional scalar mode that's evolving in the course of the density as well. And in those equations, in that first equation in that second bullet there, we've got an effective mass term that when you have overdense regions, it makes that term it suppresses that fifth force term and it acts more towards general relativity, and you've got screening. But in underdense regions, the modification is allowed to be free, and so you can, and unscreened, and so you can hopefully see some of these effects more clearly. So what we did, what Chris and I did in this work was to use some n-body simulations that were developed by Baoju Li and collaborators n-body realization. So we had GR ones, and we considered 2 F of R models, which I'll call F6, which is a weaker modification closer to GR, and F5, which is more strongly modified. And in each of these simulations, they had the precise sort of nonlinear evolution of the F of R theories, so that it encodes the full effects of these theories in the dark matter evolutions. So we took these simulations with 2 snapshots. We just took redshift 0, redshift 0.5 as our sort of our straw men, and we used a wide void finder, which uses a watershed transform. Essentially, you raise up the density until you find these sort of transition points, and be able and define, rather than using a spherical sort of blow up a balloon until you find the size of a void. It allows for the void to have a more inhomogeneous shape. So we use this to identify voids. We did find that most of the voids, if you look at this, the eccentricities, they are roughly spherical, but we identified them in this way using this prescription. We then looked at classifying the voids, and this will be important. So we looked at voids by size, and what we found was that the vast majority, about 75% of the voids, are modest in size, so less than about 25 megaparsecs, independent of the type of cosmology. And there was really 2 types of classifications we looked at, and they're called R-type and S-type. R-type for rare and S-type for shell, I think is fair to say. And so we found that you can characterize this based on this average sort of integrated density profile out to the effective radius. And as we'll see, rare types basically are wholly in a void region, whereas the S-types have a dense shell on the outside of the void, which means when you integrate out, the integrated density can be 0, even greater than 0, even if it's void in the central region. And so what we found was 50% of the smaller voids and 75% of larger voids were in this R-type category, this rare type category that doesn't have the outer shell. Okay, so here's some examples on the left hand of some density profiles for the voids, and there's 3 types of lines here. Blue is for the smallest voids. Orange is mid-sized voids, so 25 to 35 megaparsecs, and green is the larger voids that we considered out, an average of 50 megaparsecs. And there's 2 theories shown here: the GR model, which is the full line, and then the dot dash is the F5, the most strongly modified model. And what you can see here on the left-hand side are the R-type voids, which they have a void in the central radius, and then they come out with a very mild, they're almost just 0 density for the most part in the outer regions, whereas on the right-hand side you see the S-type voids that have a significant shell outside of the void region that can affect the dynamics. And this is showing you the voids for the density profiles based on the halos and based on the dark matter particles below. And what you can see is in each case there's very little difference in the density profiles from between the 2 scenarios. So we're not necessarily using the density profiles as a distinguisher between the theories. However, if you then look at the velocity profile, the velocities of the galaxies, well, here we're using dark matter halos as traces for the galaxies, you find that in particular for the smallest voids, so the left-hand sides here, the R-type voids, you do get differences in their velocity profiles. So this is actually for the particles. You can see the dark matter particles in the simulation, and you can see that as you go from GR to F6 to F5, the velocities get greater, and that's because of the differences in the gravitational potentials because of that additional 5th force. If we then look at the same result for the halos, there's fewer halos and dark matter particles, so the errors are slightly larger, but we still see for those smallest voids, we see that distinctive pattern of an increase in the velocities of those halos within the voids. And so this is just showing you the ratio of the velocities, the peak velocities in the modified gravity models relative to GR at redshift 0 and redshift 0.5. And what you can see is that, in theory, if we are able to probe the velocities of these smallest voids, they might offer the best opportunity to be able to distinguish between these models. As you go out to larger voids, there is less effect. So one thing that we then did was to try and understand this in terms of the theory, the F of R theories. We looked at both the linearized F of R models, where you linearize the mass term in terms of an effective mass term mu, and looked at it in terms of a dimensionless rate size or position variable R tilde. And then the second thing we did was to look at the full nonlinear equations to allow for the effects of screening. I won't belabor this too much, but one interesting thing you can do in looking at the linearized equations is just think about them as having effective window functions on those fifth forces. So if you look at the acceleration due to Newton, the Newtonian acceleration, and look at the fifth force acceleration, you can write them in terms of a Fourier integral over the density profile with two different window functions, and then think about where those window functions are peak. If you look at the peak density, essentially where those integrals are going to be peaked, the spatial dependency of those window functions, so that you can understand where the influence on these fifth forces is coming from. So here is a plot of that window function value that will go into that fifth force or acceleration equation. On the right-hand side is just the Newtonian one, and what you find is that it has a very monotonic, it peaks at the center, but then has a monotonic decrease as you go out. While the fifth force, the window function, actually, the peak influence for F6, the weaker model, is on these very smallest voids, which is what we saw, and then at more intermediate scales with F5, and that's consistent with what we saw in those velocity profiles, that the smallest voids are the ones that have this effect most prevalent. And it doesn't seem to change with redshift, but it does. The scale does change with the strength of the fifth force. And then finally, we did the integration analytic of the fifth forces. And indeed, as you look on the bottom level there, you can see the total force within the voids as a variation of GR, F6, and F5. And what you can see is that it's again the smallest voids, those R-type small voids, where we see the difference, the fifth force really creating that difference in the forces, which then leads to that difference in the potential. So what we're seeing in the simulations holds up with a sort of analytical interpretation of those fifth forces. Okay, so I'm conscious of the time, so I'm going to now mention the third project that we brought a paper out on recently, and this was led by Rain Liu, who is an undergraduate who is working with Nick Battaglia. She's going on to graduate school in Chicago, I believe, now next year. And then Georgios Valagianis, who is a graduate student with me, who's just recently started a postdoc at Harvard. And this is looking at constraints we might get on F of R gravity and NDGP gravity by combining two different large-scale structure traces or statistics. One is constraints on the growth of structure from cluster abundances, and the other is looking at spectroscopic galaxy clustering. So this is the idea here is combine the power that we can get from combining two complementary probes. So as I said, the first one, it's got 1 and 1 here. My bullet numbering has failed, but anyway. The first one is galaxy clustering from a DESI-like spectroscopic survey. And what we want to do here is include both linear and mildly non-linear regime clustering. We've also looked at using multiple moments here, statistics, so monopole, quadrupole, hexadecapole moments of the correlation function, coming from that as a function of redshift. And we're employing techniques that Georgios has led, along with our collaborator Aviles, to be able to model semi-analytically how these clustering, these correlation functions are modified in F of R and NDGP galaxies, not only for dark matter, but for looking at bias traces as well, so that we can employ predictions for not just the dark matter, but for what we expect to see with luminous red galaxies and emission line galaxies for a survey. And then we're using expected number counts from DESI from this paper by Font Ribeiro et al. From a few years ago. We're pairing that with predictions of cluster abundances from some recent work by Matt Madahachuril and Dylan Cromer and Nick and Miyataki and again Matt as well, to look at these from a CMB S4-like survey. This is now constrained wholly in the linear regime, and we're using this in the context of what those cluster abundances would translate into constraints on sigma 8 as a function of redshift. And we're using, so they're using predictions of lensing calibration from optical surveys below redshift of 2, and then self-calibration using CMB lensing out to redshift 3. Okay, so I just wanted to give you a sense of what, from the galaxy clustering perspective, in terms of being able to accurately model what we expect to see for these correlation functions for different modified gravity theories. We're building on some work where we looked at n-body simulations of these modified gravity theories and developed a semi-analytical approach that allows us to predict what those clustering predictions are with good accuracy. And so this just shows you predictions from that previous work for a spectroscopic survey looking at both monopole, and on the left-hand side, the 3 curves, the blue, black, and red, from top to bottom, for those, sorry, not very colorblind friendly, are for different mass traces. So if we're thinking about, different galaxy selection functions, and then on the right-hand side we have the quadrupole. And so we're happy about the ability to be able to make these predictions for the modified gravity theories down into the mildly nonlinear regime. On the sigma 8 cluster abundance side, this is showing you from the paper as a function of redshift, the pale beige lines show you the estimated uncertainties from a CMBS4-like survey for this sigma 8, the deviation of sigma 8 from lambda CDM. And then the colored curves are showing you the differences in those predictions for different theoretical models, for F of R on the left and the middle, and for NDGP on the right. And the left, it's varying the magnitude, the strength of that F of R model. And in the middle, it's just varying another parameter of power law variation, this n variable. And so what you can see here is that we expect the constraining power from these sigma 8 models to be most tight from the redshift less than 2. And we expect, in the context of the F of R theories, to have the variation in F of R to be more tightly constrained than the other parameter n. So this is, I'm realizing, flitting between galaxy clustering and sigma 8, but for the galaxy clustering from DESI, the survey alone, then what this on the right-hand side here, we're just showing the Fisher analysis constraints for the more strongly modified model, F5 on the top, and F6, the weakly modified model on the bottom. And it's the constraints that would come from the lower redshift luminous red galaxy sample and the larger and larger sample and larger redshift sample of emission line galaxies in blue, and then the combination in teal. And so what you can see is that principally for the stronger modifications, which will hit at whose effect will be pronounced at a higher redshift, we're seeing constraints coming essentially wholly driven by the ELGs. But if the modification is weaker and so it really starts to become more pronounced at lower redshifts, then the LRGs can also play a role as well. So what we did was we looked at how, what are going to be the constraints on these models if we combine both the galaxy clustering data and from the CMB-S4 survey, and sorry, the galaxy clustering from the DESI-like survey, and the cluster abundances from the CMB-S4. And there's some really interesting sort of, I think, messages here about the redshift and tracer dependencies and how they can nicely interplay. So if you look on the left here, this is for the strongly modified model. And you see that the galaxy clustering, the DESI data, really drives the constraints here. That's because these effects are going to be able to be seen at the higher redshifts, and the ELG sample is able to really provide the most robust constraints. But there is some really nice complementarity as well in the bottom, where you can see those two-dimensional spaces in terms of providing nice constraints in that f of r n end result, that where while f of r is constrained by the galaxy clustering, the cluster abundances are able to break those degeneracies and provide nice constraints on that n parameter. For f of 6, however, which evolves, it will become more pronounced at lower redshifts, the galaxy clustering and the clustering abundances are playing very nice complementary roles in getting those constraints. And then finally, just for this NDGP model, an alternative modified gravity model, this has less scale dependence than the F of R theory. It's a very scale independent model. And what we find here is that the the cluster abundances are really driving the constraints here. Okay. So that was my sort of tour through 3 recent papers, where I hope I've advocated that there's both interesting statistics that require combining large-scale structure and CMB data sets, but then there's also interesting things that we can do by looking at new environments revealed by spectroscopic data for voids, and also power to combining multiple traces and multiple data sets to reveal different aspects of theories and may perhaps be able to help us constrain those parameters. So just to tie it together, there's a number of surveys. This decade is going to be so exciting in terms of having new CMB surveys with Simon's observatory CMB-S4 that are going to provide order of magnitude improvements in resolution and sensitivity, and with large-scale structure, with LSST, Euclid, Roman, DESI building on current, DES, HSC, PFS surveys. But in order to fully leverage these, to be able to test gravity, we need to couple that with precise modeling of what we need to get from observational predictions in dark sector theories, which means we need to, leverage accurate and efficient ways to combine analytic and simulation methods to understand what we might see, and trying to understand how we can search for those distinctive signatures. So developing novel statistics, new statistics that are complementary to existing ones, combining data that we have to realize new observables, like in the kinetic SC effect, trying to leverage multiple epochs, multiple tracers, and multiple environments, from voids to galaxy clusters, and using that data to be able to extract out cosmological signatures from systematics that might mask or allow us to misinterpret them. But it really does offer us an unprecedented opportunity in the coming decade from both a theorist and an observational perspective to be able to understand gravity on cosmic scales. Thank you.
All right, thanks very much, Rachel. I'll clap. I guess everyone else is virtually clapping.
Yeah, that's okay.
Yes, thanks a lot for this very interesting talk. So we definitely have time for some questions. If people can raise their hands, that would probably be best, or you can type into the chat window. I guess as people think, I can ask one question that came to mind. I was wondering, for the last part, the cluster abundance constraints, do you have to take into account the fact that so the cluster masses are calibrated with weak lensing measurements, presumably, but the theory of gravity changes, then the way that you do the mass inference through weak lensing presumably would also change in general. So is that something that you actually have to take into account?
Yeah, that's a good question. It's not something that's been taken into account. So yeah, in theory, in theory, lensing is the lensing should remain the same for but the it's not certain that the lensing and the TSC like sort of profiles will remain. The relationship between those two would be the same, and that's something actually that we're interested in looking at with got a proposal in with Arthur Kozlowski, who's been thinking about how we simulate clusters in modified gravity and whether that affects the observables and how, but it's not incorporated in this analysis, no.
Okay, thanks. Let's see, does anyone have a question for Rachel?
I know it's so hard over Zoom.
Yeah. Well, I might ask one more question, I guess. As a sort of outsider to the modified gravity world, I was wondering, do you have like a particular favorite model that you're most excited about constraining in the next decade? I mean, I know F of R has been popular off and on. DGP seems like it was more popular maybe 10 years ago.
Yeah.
I was just wondering if there's a particular hypothesis that you're most excited about testing.
I have to say, I feel like it's a bit like saying, what's your favorite fake cheese? Like I don't, or squirty cheese. Like, I don't think any of them is palatable. And I don't think any of them has really risen to the level of being, where it's a cosmologically acceptable model that is robust, is robust. We're using them as toy models that allow us to play with, simulate what their effects might be, using them as phenomenological models largely. But I don't think I have to say, it's saddening in a way that we haven't made more progress in the theoretical side of how we might describe these modifications if we want to test them. Ultimately, a decade from now, we may just be saying it's lambda CDM and GR. But in order to get there, we need to understand what the alternatives should look like in a theoretically robust way. At the moment, F of R and NDGP are practically simulatable and understandable theoretically and give us modifications, but I don't think I would ever say that either is my favorite.
Right, fair enough. Let's see, David has his hand up.
Oh, you're muted, David.
Nice talk, Rachel. Given that we don't have, a really good form of fake cheese, I would note that Oliver Zahn, some of you may remember as a cosmologist, is now working on developing fake vegan dairy products.
Oh, really?
Yes, that's what Oliver is doing. He has a company. It's kind of like FFR models. And, but the alternative is to looking at particular models is to write down things that we know lambda CDM can't do. And the one I think about is in this area is like structure growth, right? Because we know the growth rate of structure has a certain dependence in lambda CDM. And is there a similar thing you can write down with voids, where you can say, if we see this, we know lambda CDM is failing?
So I think one of the things that I have to say this, the work that we're doing with Chris is, I think just like we've been thinking about statistics that combine peculiar velocities and lensing, right? So the EG statistics, where you're essentially cross-correlating two different observables and comparing the consistency of those in GR. I think that where this might go is to think about the growth rates that are coming from dense environments, from clusters and galaxy clustering, and make predictions for what you're going to see in void environments, and and look for a statistic that combines those two and gets and looks for an inconsistency. I think that's where we want to go, and that's where this was, the original thinking was going, but this is doing it in the context of just looking at voids, whereas I think what we want to do is to look at two environments together and try and contrast them.
Yeah, no, that seems like a nice way to go, right? Because one of the basic features of GR is gravity behaves the same way in voids and dense regions.
Mm-hmm.
And these FFR models is an example of one that violates that.
Mm-hmm.
That symmetry is a nice symmetry to be able to test.
Yeah.
Cool.
Shirley.
Hi, Rachel. Very nice talk. Thanks for coming over here to talk today. And I was just curious if what we were actually having the group meeting earlier when we mentioned Tom's new method where they use the k-nearest neighbor and cross correlations, and how that's similar to the Mark correlation function or Mark Powell spectrum. And I thought both of them will be very useful for modified gravity type of stuff where the environments could be probed in these simple statistics, and I thought like those two talks today was very cool.
And I have to say, so I didn't mention it in this talk, but Georgios, a few years ago, Georgios and I looked at the application of Mark statistics, but in dense environments, not in void environments. So in dense environments, they're trying to pick that out. I have to say, though, in work we did as part of DESI we had a paper out in November with a large number of authors where we looked at simulations. The problem for us in looking at those Mark statistics is understanding halo occupation distribution functions. And so all of the interesting things that you might see in dark matter just get, as soon as you start to have to understand what those predictions are for the galaxies that you observe, essentially all of that variation can just be subsumed into if you fit the 2-point correlation function, then the Mark correlation functions essentially don't have that much freedom to deviate from it. And so we actually, while we could see interesting effects in the dark matter, once you start trying to translate that into galaxies, it becomes diluted out. And what you need to do is to look at, for example, again, marked correlation functions in the lensing and contrasting that with numbers or something like that, something where you're contrasting two things rather than using that statistic on its own. But that's why I'm thinking maybe voids and clusters might be another way to get at that. But yeah, I know I'd have to go and read Tom's paper to understand, but that's why it's nice to come and visit, like you say, you get to and also my talk today with Will as well about gravitational waves was also really stimulating.
Thank you.
Right on cue, I see that Will has his hand raised.
Yeah. Well, I should preface my question with saying that if Colin's an outsider to this field, I'm like a galactic scale immigrant or something.
The nearest neighbor.
Not nearest neighbor. But kind of sparked by David's question, I'm wondering the logic behind going for 2-point correlations as estimators of things is then you don't have to get the amplitude of the 1-point function right. You don't have to get dn dm right or dn d void size right in order to get a good estimator. And of course, it's very hard to get those amplitudes right from theory or simulation or whatever. But now I'm wondering, since every overdensity, just from mass conservation, makes a void, if you could look at the relative amplitudes, like the big overdensity amplitudes tell you something about the amplitudes of big voids.
Yes. So
I think then you can use 1-point functions directly because you can calibrate the amplitude of one species from the observations of the other one.
I think that's true. Yes, people are looking at the effect of void abundances as a test of gravity. I had expected that the density profiles would be different in those simulations, and I was surprised that they were so similar. But it's certainly, as you said, it's certainly true. Like you can apply a Press-Schechter style thing, and you will get the voids and the increased clustering will increase increased voids. There's also people thinking about going back to the idea with the CMB using morphologies and looking at connected spaces and using one-point functions in that way, and higher order statistics. And so I think one of the things we're also trying to look at the moment is the practicality of this. Obviously, by definition, in void regions, you don't have many samples, galaxy samples. So when we start to look at the DESI selection functions, are we actually going to see enough objects? What are the realities of how they trace it? And so I think using lots of different statistics, like you say, and using the different number counts, spatial scales, dynamics and correlations, I think that we're going to need all of them to try and eke out what it looks like.